All right, so in this week's lab, we're going to be calculating the amount of energy in a few different food items. So what we're really trying to get to is the amount of calories. So if you're eating food and you look at your nutritional label, you're looking at the back to see the amount of calories in that food. What you're really looking at is to see how much energy is in that food, right? So with our focus this week on energy and the molecules that provide us with that energy, we are going to be using fire to calculate the amount of heat energy that's produced as we burn the food items. And what we're trying to get down to is how much energy is in each gram of food item. And the three food items we're burning are peanut, marshmallow, and potato chip. And the unit again is the calorie. But there is a difference between a lowercase calorie and an uppercase calorie. So in science, the calorie is a little c, right? The calories on the back of your food labels is a big C. It's called a kilocalorie, but they use a larger capital C to represent that. By definition, the scientific term of a definition of a calorie is the amount of heat energy required to raise the temperature of 1 gram of water by 1 degree Celsius. So you will be measuring the temperature of water inside of the can. It'll be right above the food items you burn. So as the food items burn, the heat will be released, making contact with the bottom of the can and changing the temperature of the water inside, and that you'll be able to measure. So again, little c, science calories, big C, food calories, right? So when you look at them, their relationship to each other, a science calorie is equal to 1,000 science calories is equal to 1 kcal, also written as a capital C. So when you see your data today, you'll see thousands of calories, and you'll go, Miss Alsop, there's no way that in 1 gram of a peanut there's 1,000 calories or several thousand calories. And there is, but they're science calories, and you have to divide your answer by 1,000 to get to a number that would make sense, right? So when you're saying, okay, in a gram of a potato chip or a gram of a marshmallow, there's probably a handful of calories. So originally, your early answer will look way too big to be possible, but you're going to divide that by 1,000 to convert from a science calorie to a food calorie. Okay, so the materials that are used are listed here. We're going to be seeing the temperature measured by a thermometer. We have a balance to measure the mass of each of the food items because we want to know per gram, so we have to know how many grams are in the food items. There'll be a structure with a ring and a ring stand that you'll see in the video. We have a metal can to hold the water. I'll be using a lighter to ignite the food items. There's a little cork and pin foil apparatus to basically hold the food in place. There's a stirring rod to hold the can in place, and also an extra stirring rod to mix the water as the fire goes. I used a ruler to measure the distance from food to can, and then the graduated cylinder was used to measure out the 100 milliliters of water that I added into each can. So those items were all used. The procedure is shown below. Basically, you're going to watch me weigh each food item before burning. You're then going to see the initial temperature of the water before any heat is released. I'll then pin the food item below the can, light it on fire, and then once the fire burns all the way through the food item and the flame goes out, I will then look at the thermometer again to find what's called the final mass. So you'll have an initial mass before burning and a final mass after. You'll have an initial temperature before burning and a final temperature after. And those are the pieces of data we're going to use to calculate the amount of calories. So because we want to know calories per gram, we're going to get the total amount of change in temperature, and then we're going to get the total amount of calories by looking at how many grams burned overall. We'll get to the actual calculations in just a little bit. If we had been doing this in class, we have a warning to make sure that your fingers are not in the way and that we pulled all our hair back so that we don't ignite any of those other unintended items. You'll repeat the same procedure for the 3 different food items. So you'll be registering or recording a starting temp and a final temp for each food item, and a starting mass and a final mass for each food item before and after the burning process. Again, just a kind of hopefully blinking star here that there are 1,000 of those science smaller calories for every 1 food calorie, also known as a kcal. Okay. Before you get started, you want to answer, why are we doing this? What are we trying to determine? And you want to fill out your EXT, right? We're comparing 3 things. What are those things? How many trials will there be? What's the difference between my groups? What are we measuring? Which group would be a control group? I'll tell you right now, I'm going to give you one kind of giveaway answer. There isn't a control group for this experiment, and that's rare, but it does exist. And in this group, we don't know any prior information about our 3 food items to be able to say, okay, since we know how many calories are in this food item, we're going to compare the others to that group. They're all unknown. So we don't have a control group. We don't have a zero group. So there will not be a control group. So you can fill that one in as NA or none. You need an if and then hypothesis, your title following the formula, the effect of, and fill in that IV on, fill in your DV, and then look back at the procedures. My tip here for constants, if you can think of some already off the top of your head, great. If you're struggling, go back to the procedure and read through what steps are done the same for each of our different food items. We need 4 constants as always. Okay, this is the visual of what we'll be using as the setup, right? Here's the ring stand, here's the can being held in place by the stirring rod, here's the little pin zoomed in up here. This is the cork with the foil, or little pin, that's where the food will be placed. It's right, kind of poked right on the top of that pin underneath the can. But you'll see that in the video shortly. So here's your data tables. You have the same table and the same calculations for each food item. They're just in alphabetical order: chip, marshmallow, and then peanut. We have a space for the starting and final mass. Here's the calculation for the difference. And notice it's absolute value, meaning there is no negatives, because it will lose mass during burning, but that's not indicating negative calories, right? That's just showing the amount of energy released. So absolute value, your change in mass; absolute value, your change in temperature. Okay, I'm starting temp, final temp. And so then these boxes that are highlighted are the pieces of information that you're going to need below. So for each step, you have the equation and then a place to fill in your data. So you're going to type in and complete your data table, and then you're going to fill in these blanks as you go until you get to your final answer down here in orange. So to figure out your calories, you have your total calories to start, which is the mass of the water. So you have 100 grams of the water times how much the temperature changed. So if it started at 40 degrees and went to 45, you'd plug in 5 there, right? Whatever it says in this green bar. So you'd plug in that change in temperature, and I try to use the color coding system to show you which one's which. So here's change in temp, that goes here, right? You take 100 times your change in temperature equals your amount of total calories, science calories, right? You then take that purple answer, you move it down here, and divide by your red change in mass, which is found right here. You plug that in where it's red, right? That will give you how many calories per gram, but I'm still in science calories, those big numbers. So this should be in the thousands. This number's big. If it's small, something's wrong, right? So then you have your calories per gram, your science calories per gram, and the last step is to then carry those down, divide by 1,000. Again, this will give us those food calories that we're used to seeing on the back of our nutritional bags, wrapping labels of some kind, right? And this is your final answer, and you want to round it to the nearest whole number. Nearest whole number. You repeat the same thing for marshmallow and peanut, right? So I'm not going to go through it again, but just very carefully follow the steps, plug in, use those color coding tips to help you know which one's which and where to plug things in. And then it's time to analyze, right? What did we find out? What did the data show, right? Before you get started, I want you in your own words, not go back up and copy and paste the scientific definition, but read that definition if you forgot it, and then simplify that into what we call layman's terms, right? Common terms. In your own words, what are we saying here? What's a calorie, right? Question 2 is based on the Actively Learn article that we should have already read, and I'm gonna recommend that you pause and go look at that article if you haven't, because this question is really vital to being able to complete your clear. So which of the macromolecules, and remember the macromolecules that are available include carbs, lipids, or proteins. Those are our 3 energy sources in food. So which one contains the most calorie or energy, right? That's what we're really looking for. And then after you've completed those 2 questions, it's clear time, right? Here's your question. Which food item contained the most calories per gram? Name the food, tell me the calories for each food, quantify the difference between how many calories, and then lastly, why. Why does that food have the most, right? Again, you need that article as background for knowing why that food should have the most energy. Okay? And that is all. Once you've completed those pages, you can submit and upload your finished doc. You should be working in breakout groups to have discussions and help each other out. However, each and every one of you need to upload your own individual document, right? So this time, if someone's not talking, not sharing, not helping, they're on their own, and you are only responsible for submitting your document. Hopefully you're working through this together and you're, again, bouncing ideas, clarifying things. If you're still stuck, calling me or Mr. Owen to say, hey, can you clarify something? Can you help us out? But we want you individually to understand how and why we're doing this. Okay, so we're not splitting the roles. We're not saying you do part one, I do part two. We're working through it together. All right, here we go. All right, so here are our 3 food items. So you have a peanut, a marshmallow, and a chip. Those are the 3 items we're going to burn to calculate the amount of calories. Here's the balance. We'll weigh their starting mass before burning and then again after burning. We have our apparatus here that has the ring stand with the can, which contains 100 milliliters of water, and the pin for each of the food items to be attached to. We also have a thermometer and a lighter so that we can measure the change in temperature and get the foods on fire. So we're going to use those tools in order to calculate, again, the amount of calories. Okay, here we go. Alright, so we're going to start with the chip. We're just going to go in alphabetical order. Chip first, its initial mass, or starting mass, is 0.82 grams. And that's before burning. I also want to find out what's my starting temp. So I'm going to go ahead and put the thermometer into the liquid, into the water in the can. 22 degrees. Let's make sure it stabilizes. Alright. We will round to a whole number. So 22 degrees will stand. Okay, 21.8 rounds to 22. And we'll go ahead and take that out because we don't want to heat the thermometer. And now we'll attach the food item and get it going. Okay, my chip is in place and I'm now ready to start the burning process. So I'm going to go ahead and turn on the flame. I'm going to wait until it actually lights on fire. And in order to get the total calories, I need to make sure that it burns all the way through. So the chip is now on fire. I'm going to let it burn. If for some reason it goes out, I will relight until the chip has burned all the way through. And while it is burning here, I'm going to go ahead and continue to stir to just distribute the heat throughout the water in the can. So make sure I'm going to just keep mixing it. I've got a little campfire going on here. The chip is fully engulfed there. And make sure that we keep distributing that heat, mixing it all around. The water gets evenly heated. I think you can see why I didn't ask you to try this at home. And I do not encourage you to do so. But it does have a nice little campfire smell there. All right. And our chip has burned all the way through. And I'm now going to get a final temperature. And we're going to wait until it stops so that get an accurate count here. Starting to slow down. All right. We're going to call that 35. As it approaches, it seems to be slowing down, but that would round to a 35. Okay, so 35 degrees Celsius. Okay, so now we can see the final mass. We have the remnants of the chip. They broke apart as they were being pushed off of the pin they were on, but that's okay, the mass is still there. They're just now in pieces. And all that remains is 0.04 grams. So that's our final mass of the chip. Next up, as we move along in alphabetical order, we have the marshmallow. And our marshmallow's initial mass is 0.79 grams. I'm also going to re-measure temperature because the temperature is starting out at a different number than it started when we had our chip. So the new initial mass, again, we'll let it get to its final count. And once it does that, we'll record our initial mass. So slowing down. Okay. See if it gets to a 0.5, we'll round up. Yes, okay. So we're going to register this as a 34 degrees Celsius. Again, round to a whole number here. 34 degrees Celsius. And our 0.80 again for the mass. Once again, we now have our marshmallow in place. I'm going to go ahead and start the flame. Once it lights on fire, I will continue to make sure it burns all the way through, again stirring like last time, so that the water in the can gets the heat evenly distributed until the marshmallow has burned all the way through. And this is going to make our room smell like a campfire. And extinguished. Go ahead and find our new. Okay, if you have a fire pit in your backyard, might want to make some s'mores tonight because this smells really good. I wish I had smell-o-vision for you. And we'll let it get to that final temp before we pause for the marshmallow here. It's still climbing. Seems to be slowing, but let's see if it gets to 37 or 38. And it seems like it's holding, so we'll put 37 as our final temp for the marshmallow. And for the final mass of our marshmallow, looks like 0.48 grams for that, again, charred remains of the marshmallow. All right, and now last is our peanut, coming in with an initial mass of 0.74 grams. And our initial temp before burning, we'll round that, 35 degrees before we light the peanut here. Okay, so now we have the peanut in place, and we're going to go ahead and light our third and final item. And again, I'm going to hold the flame until the item ignites, and then I'll start stirring the liquid inside the can to evenly distribute the heat until the flame goes out. The thing about doing this digitally is that anyone with a peanut allergy does not have to be excluded from this experiment. And we don't have to change our food items. For that, again, the opposite of our marshmallow, we're glad there is no smell-o-vision here. Besides the calculation of calories, we can also make note of the amount of time it takes for items to burn up. That doesn't indicate necessarily the amount of energy, but it does tell us the amount of time that the energy would last in the body, so how quickly it would burn up. You may have heard of foods that contain a quick or a long-lasting source of energy. So this is not the amount, but it can give us some clues as to how long the energy would last. And that flame is starting to go out. We're almost there. And there we are. Okay, so let's go ahead, insert the thermometer, and see what we got for our final temp. Still climbing there. We're up to 56. Let's see how many more it goes. Okay, it is starting to slow, so we might be done here at 57. Let's give it a couple more seconds to see if, oh, it's actually dropping. So we'll stop at 57 degrees. And like our chip, our peanut broke in half as it came off the pin there, but that shouldn't change our mass. Its final mass is 0.06 grams. Okay, so now you have data for both mass and temperature of all three food items. You can use your calculations to calculate the amount of energy per gram.